Hello students, this is part 1 of Units and Measurements, which is the first chapter for 11 Standard Physics. This is mainly meant for competitive examinations like NEET, IIT, KEAM, etc. based on NCERT syllabus and for courses like CBSE, ICSE and all. So since it is meant for competitive examinations mainly, we have moved a little bit out of the syllabus so that you will be able to cover any kind of questions asked for the competitive examinations. Now let us move to the syllabus. Physics is a quantitative science based on measurement of physical quantities. When something is called a quantitative science means that it involves numbers. When some physical quantity is measured, it is to be converted into numbers. Measurements involves maths and physics. Physics because actually fundamental laws of nature are involved. Maths because numbers are involved. Then both together will give the measurements. Understanding the laws of nature of physical world, we need units. So these unit and measurements are fundamental to all sciences. When we say magnitude of physical quality, that involves a numerical value and a unit. Why we need units? Units are required to compare objects. When we compare objects, we say something is small. For example, smaller means in size, for example, or in weight. Okay. Or we are saying shorter. That means shorter in length, for example. So when we say light, heavy, lengthy, something like that, that then naturally we need units to compare this. We measure each physical quantity, example length, in its own units, example meter, by comparison with the standard. When we say the length of an item is 1 meter or 5 meters, then we are comparing it with the standard of 1 meter. So there should be a standard which will not change, which is constant. So in the case of meter, we are taking the speed of light, which is a non-constant. Okay, speed of light in vacuum. We know that speed of light in vacuum is 3 × 10⁸ meter per second. It's not exactly 3, okay, but approximately equal to 3. 3 × 10⁸ meter per second. That means per second, the light in vacuum will travel 3 × 10⁸ meters. Okay, so in 1/3 × 10⁸ seconds, the distance traveled by light is 1 meter. Base standards must be both accessible and constant in nature and which do not change by changing the measuring parameter. Now let us say that, okay, the mass of an object is 10. What does that mean? 10 can be 10 milligram, it can be 10 kilogram, 10 gram, and 10 ton, 10 quintal, whatever. So when we say 10 or a numerical value, it should be associated with the unit also. See, by milligram, when we are saying actually, if you're going to a jewelry, you may be asking for milligram. But if you're going to a kirana shop or maybe some other shop, okay, for buying rice or something, then you have to say in kilogram only. You cannot go and ask the rice in milligrams. So different units are required. Smaller for measuring small objects and big and bigger objects. When we write 10 kilogram and 10 gram, even though magnitude is the same, both the cases it is 10, but the units are changing. One it is kilogram, one it is gram, and we know that 1 gram is 1/1000 of a kilogram. Unit gives us the facility to compare physical quantities. Then what is a physical quantity? All the quantities which are used to describe the laws of physics are called physical quantities. Yeah, and these physical quantities should be measurable. Okay, and the measurement of any physical quantity involves comparison with a certain basic accepted reference called unit. Okay, this is what I told at the beginning. Actually, for meter, we are taking the velocity of light in vacuum. Let us take three basic physical quantities: length, then mass, then time. Length is measured in meter, okay, mass in kilogram, and time in seconds. Now, for measuring length, we are not using the same unit for all the cases. For some cases, we need a smaller unit. Another case, we need a bigger unit. So let us take the case of a small ant. If you want to measure the length of an ant, we don't have to use a meter scale or centimeter scale. The length of an ant may be in millimeter. Okay, it may be 3 or 4 millimeter. Okay, in that case, we will use it 1 millimeter. 1 millimeter is 1/1000 of a meter. But if you want to measure the length of a squirrel, that will be maybe 15 to 20 centimeter or so. For that, we will be using centimeter, the unit centimeter we are using. And if you want to measure the length of a lion, we will be using meters. And if it is a rod, we will be using kilometer. And if you want to measure the distance from a star, we have to use light years. What's the light year? Light year is actually the distance traveled by light in 1 year. Okay. But suppose we want to measure the length of a, the size of a cell. Okay. If you want to measure the size of a cell, then we have to use micrometer, that is 1 millionth of a meter. And if you want to measure the size of a hydrogen atom, we will be using nanometer, that is 10 raised to minus 9 meter. Similarly, in the case of mass, we have units like gram, kilogram, 1000 gram is 1 kilogram, then 1 quintal. Quintal is actually 100 kilogram. 1 ton is 1000 kilogram. And if you if you want to measure smaller objects, you may go to milligram, 1/1000 of a gram. Then microgram, 1 millionth of a gram. Then there is such a 10 raised to minus 10 gram is 1 nanogram. Suppose we are going to a jewelry and we want to buy some gold, then we may be using milligrams there. Okay, but if you want to buy rice, then we will be measuring in kilogram. Okay, we may not use actually milligram for rice. Okay, so the unit differs depending upon situation and requirement it will differ. Now you take the case of seconds. Seconds can be 60 seconds is 1 minute, and 60 minutes is 1 hour, 24 hours is 1 day. Okay, like that it is going. And we know that actually 365.25 days is 1 year. Okay. Now there is millisecond, mean 1/1000 of a second. Then there is microsecond, 1 millionth of a second is actually microsecond. Then 10 raised to minus 9 second is 1 nanosecond. This is how it goes. Okay. So as I told you, 1000 kilogram is 1 ton, and 1 quintal is equal to 100 kg. Okay, and if you want to, how will you find 1 light year? 1 light year is actually distance traveled by light in 1 year. That is 365.25 into 24 into 60 into 60 into 3 into 10 raised to 8 meters. That will come about 9.461 into 10 raised to 15 meters. We cannot use the same unit for all the measurements. So we have to multiply the standard units with the whole numbers or with fractions to make suitable units. You take the case of meter. Meter is unsuitable for many measurements. You cannot measure the distance between two heavenly bodies, between two stars. You cannot use meter. For that you have to use a bigger unit like light year. Okay, now same way you cannot use meter for measuring the size of an atom. Okay, you need a lesser unit for that. So it is too small to measure the distance between heavenly bodies or distance between towns. For measuring the distance between two towns, we need kilometers. Okay, and it is too large to measure the dimensions of the elementary particles which form the atoms and the atomic nucleus, or to measure the wavelength of light. Thus the meter must be transformed into multiples or fractions of length. Multiple units are derived from fundamental units by multiplication by integer, just like kilometer. You multiply meter by 1000, you will get a kilometer. Submultiple units or fractional units are derived from the fundamental unit by division by an integer. 1 centimeter is equal to, as you know, that 1/100th of a meter, 0.01 meter. 1 millimeter is equal to 1/1000th of a meter, that is 1.001 meter. 1 micron is equal to 10 raised to 6 meters or 1 millionth of a meter, and 1 millimicron or nanometer is equal to 10 raised to -9 meter. Now there is units like astronomic units, which is the distance between Sun and Earth. 1 AU is equal to 1.496 into 10 raised to 11 meter or 1.5 into 10 raised to 12 meter. And there is units like light year, as I mentioned earlier. It is the distance traveled by light in 1 year. 1 light year is equal to 9.461 into 10 raised to 15 meter. Now let us see how physical quantities can be classified. Now, based on directional properties, physical quantities can be classified as scalar, vector, and tensor quantities. Scalar means you know that the quantities having only magnitude, just like mass, time, pressure, speed, and distance. Vector quantities means those quantities which are having both magnitude and directions, and we are using vector algebra for the operations of these vector quantities. Now, examples of force, momentum, acceleration, velocity, and displacement. Okay, and tensor quantities require, apart from this magnitude and direction, it requires a plane to act. Tensor quantities are physical quantities that are neither scalars nor vectors, requiring a description of magnitude, direction, and plane or surface where they operate. Examples of tensor quantities are stresses, strain, moment of inertia, conductivity, electromagnetism, etc. All these require some plane to act upon. Based on the dependency, the physical quantities can be classified as actually base quantities or derived quantities. Base quantities are having independent existence actually. They don't require any other quantities to define them. Okay, this base quantities does not require, they do not require any other quantities to define them. They have independent existence. But derived quantities are derived from the base quantities. The accepted system of units is actually System International or SI systems unit. Okay. Now each base quantity is defined in terms of certain basic arbitrarily chosen but properly standardized reference standards called unit. There are some properly standardized reference units are there. Okay. So in System International or SI system, there are 7 base units are there, such as meter, kilogram, second, ampere, Kelvin, mole, and candela. We know that a meter is for length, kilogram is for mass, and second is for time. Ampere is for measurement of current, and Kelvin is for thermodynamic temperature, and mole for amount of substance, and candela is for intensity of light. So the units for fundamental base quantities are called fundamental or base units. And apart from that, in SI unit, there are 2 supplementary units also. They are called angle and steradian. So this plane angle and solid angle. Okay. Plane angle is measured in radian and the solid angle is measured in steradian. Those physical quantities derived using the base quantities are called derived physical quantities. Okay, derived units. And there can be combination of the base units and derived units also. A complete set of units, both fundamental and derived units, are called system of units. For example, you take the case of volume. Volume, you know that actually is distance into distance, or LBH, length, breadth, height, we are saying. Okay, that means it's a multiple of 3 lengths. Okay, so that is a volume. It's actually 3 fundamental, meter is a fundamental unit, or 3 times we are multiplying meter, so we are getting a cube of a meter, that's the volume. Okay, so density is actually mass per volume. So mass is a fundamental unit, whereas volume is a derived unit. So using these two, one base unit and derived unit, you are getting another derived unit. Like that, it goes on. To define the derived quantities or derived units, we require fundamental units or fundamental quantities. Okay, let us take some examples. Force, for example, you know that the force is mass into acceleration, and acceleration is again distance by time square. So distance is a fundamental unit, time is a fundamental unit, mass is a fundamental unit. So from using these three fundamental units, you are making a derived unit. Okay, so mass into distance by time square, or mass into length by time into time. So like that we are deriving force. Just like if you take another example, let us take volume. Volume is, as we discussed before, LBH, length into length into length, length into length into length. So we are taking meter as the length of path traveled by light in vacuum during a time interval of 1 by 299,792,458 of a second, or you can say 1 by 3 into 10 raised to 8 of a second. Okay, that is the distance traveled by light in 1 by 3 into 10 raised to 8 seconds. This time interval was chosen so that the speed of light sees exactly 299,792,458 meter per second. It is actually measured precisely. So it is sensible to adopt the speed of light as defined quantity and to use it to redefine the meter. The derived units are combinations of the fundamental units. So derived units in physics are units of measurement derived from the 7 base units of the International System of Units, SI system of units. We told actually, we just mentioned that there are 7 base units in SI system. Okay, So using this, we may manipulating this or using this by adding or maybe multiplying by dividing. So we will make actually different derived units. So by combining base units in various ways, maybe you can say multiplication, division, or exponentiation, like that, we can make derived units. Examples of derived units, we can say actually velocity. Velocity is actually distance by time, okay, or displacement by time. Or force. Force is equal to mass into acceleration. Acceleration itself again distance by time square. And energy. Energy is the force into distance. Like that, we can make different derived units. The units responsible to define the derived quantities are called derived units. Now, you know that velocity is distance by time, then force is mass into acceleration, like that you can make, and the unit of force is Newton. Okay, like that you can make different derived units. The most commonly used unit in science and technology is actually SI system of units, the System International. Okay, it consists of 7 base quantities and corresponding units. We know that length is measured in meter, mass in kilogram, time in second, temperature in Kelvin, and electric current in ampere. Okay, and amount of substance in mole, then luminous intensity in candela. Okay, so let us see what are the essential requirements of a unit chosen. So when we choose a unit, it should be of suitable size. So if you want to measure gold, we will be using milligrams. We will not use kilogram for measuring gold. But if you are going a stationery store, you are using grams or kilogram for measuring the items there. So it should be accurately defined. Okay, we told actually the speed of light in vacuum is used to define meter. Then it should be easily accessible. Okay, then it should be easily reproducible, just like actually the scale, meter scale. Okay, it is easily reproducible. Then it should not change with time. The standard should not change with time. Okay, if you're measuring something in the morning, it is one quantity, and in the evening it is another quantity. That should not happen. The quantity should not change with the time, and should not change with the changing physical condition like temperature, pressure, and all. Okay, that will not change with the temperature, pressure, or something. So something, for example, you are measuring the length of an item here, then you are taking to US, it is changing. Okay, here it is 1 meter, there it is 1.2 meters. That should not happen, but it should be constant. That shall not change. Because we have clearly defined, and based upon the standard defined, it should be fixed. Now let us see how the units are classified. So units are classified as fundamental or base units, derived units, supplementary units, and practical units. We have already seen the fundamental base units and derived units and supplementary units we have seen already. So we know that in SI system of unit there are 7 fundamental base units like meter, kilogram, seconds, then Kelvin for temperature, then mole for the amount of substance, then candela for the luminous intensity. Okay, then ampere for current. So 7 base units are there. Now let us see what is a mole, because we know that what is meter, what is kilogram, seconds, and all the things we know, but whatever we are not familiar with, we will just see. So one mole contains exactly 6.022140076 into 10 raised to 23 elementary particles. The elementary particle means it can be an atom, it can be an ion, it can be molecule, or it can be electron, or any other particles, or a specified group of particles. Okay, so this Avogadro number is a fixed numerical value of the Avogadro constant Na when expressed in the unit of mole raised to -7, and is called the Avogadro number. The amount of substance N it will change, because it can be an atom or molecule or an ion or an electron, as I mentioned earlier. The n, the amount of substance n of a system of in a system is a measure of the number of specific elementary entities. Okay, so it will change. So as I said, it can be atom, molecule, ion or electron, anything. It can change because that it will change as per the situation. So when the mole is used, the elementary entities must be specified, because you should specifically say whether it is an atom, molecule or ion. You can specify, then only it will be clear. Okay, so 1 mole of oxygen means 16 grams, which is the atomic mass. 1 mole of aluminium is 26.98 grams, which is the atomic mass, and it will contain 6.022 in 10 raised to 23 atoms. 1 mole of copper will contain 6.022 in 10 raised to 23 atom, and that means 63.55 grams. That means the atomic mass is 63.55. So in 63.55 grams of copper, there will be 6.022 into 10 raised to 23 atom. Similarly, the atomic mass of aluminum is 26.98. Therefore, in 26.98 grams of aluminum, there will be 6.022 into 10 raised to 23 atoms. Likewise, for carbon or graphite, the atomic mass is 12.01. Therefore, 12.01 grams of carbon will contain Avogadro number of atoms. So, then 1 mole of oxygen molecules, 1 mole of oxygen molecule, one oxygen molecule will contain 2 atoms. That means it's 32 grams. Okay, so 32 grams of oxygen molecule will contain Avogadro number of oxygen molecules. The SI unit of concentration of the amount of substance is the mole per cubic meter. Mole is a unit of amount of substance, which is fundamentally a count of discrete entities. Just like we say 1 dozen will contain 12 of something, a mole will contain Avogadro number of something, that is 6.022 in 10 raised to 23 or something. If you say 1 mole of oxygen, it is not clear. You have to specify whether it is 1 mole of oxygen atom or 1 mole of oxygen molecule or ion. Like that you have to specify. So when you say 2 moles of hydrogen molecules combined with 1 mole of oxygen molecule to give 2 moles of hydrogen molecules, it is clear. Otherwise, you have to say, 4 moles of hydrogen atom will combine with the 2 moles of oxygen atoms. So, without specifying this, calculations involving reacting quantities would be impossible to lead to correct results. Now let us see what is candela and what is luminous intensity and how it is measured. Luminous intensity is a measure of the brightness of a light source, specifically the amount of light emitted per unit solid angle. It is the amount of luminous flux or light emitted from a point source within a given solid angle, and it is measured in candela. It describes how much light is emitted by a light source in a specific direction, not the amount of light it generates overall. In the figure you can see there is a light source and it is emitting light in the unit solid angle. Okay. So luminous flux is the total amount of light emitted by a source, whereas luminous intensity is the amount of light emitted in a specific direction. Candela is the SI unit of luminous intensity, and it is defined as the luminous intensity in a given direction of a source that emits monochromatic radiation of a frequency 540 into 10 raised to 12 hertz and has a radiant intensity in that direction of 1 by 683 watts per steradian. Monochromatic means actually having a single frequency. Now let us see some practical units which are not part of the SA system of units, but it is practically used and and can be converted into SA units. One light year. Light year is the distance traveled by light in 1 year. That is 365.25 into 24 into 60 into 60 into 3 into 10 raised to 8 meter. That is the speed of light. It will give 9.46 into 10 raised to 15 meters. 1 mile is 1.609 kilometers, and 1 cent we are using to measure the area of land, 40.47 meters square. 1 hour is equal to 100 meters square. Okay, and 1 hectare is equal to 10,000 meters square. 1 horsepower is equal to 746 watts. Now let us see some practical units written outside SI. So we know 1 minute is 60 seconds and 1 hour is actually 60 minutes into 60 seconds, that is 3600 seconds. 1 day is 24 hours and 1 year is equal to 365.25 days, and which is equal to 3.156 into 10 raised to 7 seconds. 1 degree, you know, it is pi by 180 radians, because the maximum angle that can be subtended at the center of a circle is 360 degree, which is equal to 2 pi radians. From that we can derive what 1 degree is equal to pi by 180 radians. 1 liter is equal to 10 raised to minus 3 m cube, and whereas a ton is 1000 kg and 1 quintal is 100 kg. 1 carat is 200 milligram. This is mainly we using for measuring the weight of diamonds and all. Okay. For gold we are using milligram. So 1 bar is equal to 0.1 megapascal, which is 10 raised to 5 pascal. 1 curie is 3.7 into 10 raised to 10 per second, and 1 Roentgen is equal to 2.58 into 10 raised to minus 4 coulombs per kilogram. These are these units we are using radioactive materials. 1 barn is equal to 100 femtometer square, which is equal to 10 raised to 28 meter square. 1 femtometer is equal to 10 raised to minus 15 meter. 1 R is equal to 100 meter square. 1 hectare is equal to 10,000 meter square, which is equal to 2.471 acres. 1 acre is equal to 100 cents, which is 4,047 meter square. 1 cent is equal to 40.47 meter square, which is 1 by hundredths of an acre. These units we are using for measuring the area of land. Now standard atmospheric pressure is 1.013 into 10 raised to 5 pascal. Let us see some of the rules for writing units and their symbols. If one unit is in honor of a great scientist, and that should be written in small letters. Okay, for example, Newton. Newton should be written as Newton, and N should be small letter. But if you are using the approved abbreviation, for example, capital, N, it should be capital. For ampere we are using A, and for watt we are using capital W. Okay, and for ampere we are using capital A. The symbol of unit should be written either in full or in agreed abbreviation. For seconds, we are writing the agreed abbreviation of S. You should not write it as SEC. You should write second fully or S. Now, no hyphens shall be used in units. For example, Newton hyphen meter is not correct. It should be Newton space meter. Not more than one slash shall be used in a unit. For example, meter per second square, you cannot write as meter per second per second. It is better to use meter second raised to minus 2. No full stop to be used after unit. For example, Newton dot is not allowed. It should be capital N or Newton in small letters. For measuring very small units of length, we use micron. Micron is 10 raised to minus 6 meter, or nanometer 10 raised to minus 9 meter, angstrom 10 raised to minus 10 meter, or Fermi. Fermi is 10 raised to minus 15 meter. Okay. So Fermi is usually used to measure the size of nucleus or atoms or etc. Now, the smallest unit of area is barn. One barn is equal to 10 raised to minus 28 meters square. It is used for measuring the cross-sectional area of a nuclei. For measuring higher lengths, we use solar day, for example. It is the time taken by Earth to complete one rotation about its own axis with respect to the Sun. Or we use the sidereal ray, which is the time taken by Earth to complete one rotation about its axis with respect to a fixed star. Then solar year is the time taken by Earth to complete one revolution around the Sun. One solar year is equal to 365.25 solar day, whereas a sidereal ray is equal to 365.25 sidereal ray. Lunar month is the time taken by Moon to complete one revolution around the Earth. One lunar month is equal to 27.3 days. One shake is 10 raised to minus 8 seconds. We use different prefixes in SI system of units to express the units. For example, 10 raised to 1 is deca, whereas 10 square is hecta. Okay, 10 square is hecto, then 10 cube is kilo, 10 raised to 6 is mega, 10 raised to 9 is giga, 10 raised to 12 is tera, 10 raised to 15 is peta, and 10 raised to 18 is exa. If you go for smaller units, then 10 raised to minus 1 is deci, 10 raised to minus 2 is centi, 10 raised to minus 3 is milli, 10 raised to minus 6 is micro, 10 raised to minus 9 is nano, 10 raised to minus 12 is pico, 10 raised to minus 15 is femto, and 10 raised to minus 18 is atto. We have already discussed there are 7 base quantities in SI system of units, the international system of units. So for time it is seconds, symbol is S, length it is meter and the symbol is M, mass it is kilogram, symbol is kg, and electric current it is ampere, symbol is A, capital A, and thermodynamic temperature it is Kelvin, capital K, amount of substance it is mole, MOL, and for luminous intensity it is cantella CD. Okay, system international units. In system international units, 1 mole is the amount of substance containing the same number of elementary entities. It can be atoms, molecules, and this thing we have already discussed. Okay, as there are atoms in exactly 12 grams of carbon 12. Okay, and it is equal to Avogadro number, which is approximately 6.022 into 10 raised to 23. 1 light year is the total distance traveled by light at a speed of 3 into 10 raised to 8 meter per second in vacuum during 1 year. That is 1 light year is equal to 365.25 into 24 into 60 into 60 meter. That is 9.461 into 10 raised to 15 meter. The distance to the nearest star, a faint red dwarf star, Proxima Centauri, is 4.2524 light years. 1 astronomical unit, which is the mean distance between the Earth and Sun, is 1.496 into 10 raised to minus 11 meter, or approximately 1.5 into 10 raised to 11 meter. Okay, 1 astronomical unit is 1.496 into 10 raised to 11 meter. Now let us see what is an astronomical unit and what is a parallactic seconds or parsec and what is AMU. A standard astronomical unit is the parsec, which is the largest unit of length. 1 parsec is the distance at which there is 1 second between two objects that are separated by a distance of 1 astronomical unit. Okay. In other words, it is the distance at which the arc length of 1 astronomical unit subtends an angle 1 second at a point. 1 arc second is equal to 1 by 3600 of a degree. It's also equal to 1 by 60 of an arc minute, which is 1 by 60th of a degree. In radian, the arc second approximately 4.484 into 10 raised to minus 6 radians. So in the figure you can see the sun makes an angle of 1 second with the with Earth. Okay. So the distance, 1 parsec is the distance, okay, from one point to the sun, which makes an angle of 1 second. So 1 parsec is equal to 3.084 into 10 raised to 16 meter. Is equal to 3.084 into 10 raised to 16 meter divided by 9.461 into 10 raised to 15 meter. Okay, that means 3.26 light years. Okay, so when we convert 1 parsec in light years, it will be 3.26 light years. Okay. So when we convert it into astronomical unit, 1 parsec is equal to 2.06 into 10 raised to 5 astronomical unit. The masses of atoms can be compared with one another more precisely than they can be compared with a standard kilogram. So for this reason, we have a second mass standard, which is the carbon-12 atom, which is internationally, which is by international agreement has been assigned as the mass of 12 atomic mass unit. That means one AMU is 1 by 12th the mass of carbon-12 atom. The relation between the two units is 1 unit is equal to 1.66053886 into 10 raised to 27 kilogram. Okay. 1 AMU is used to measure the mass of atoms and molecules. So at the center of a circle, 360 degrees is formed. So 1 degree is 1 by 360 of a turn. Okay. So 1 arc minute is 1 by 60th of a degree, and 1 arc second is 1 by 60th of an arc minute, which is 1 by 3600 of a degree. So milliarc second is actually 1 by thousands of an arc second. So micro arc second is equal to 1 by 1 million of 1 arc second. 1 AMU is defined as 1/12 the mass of carbon-12 atom. 1 AMU is approximately equal to 1.66 into 10 raised to minus 27 kilogram. We know that electrons have negligible mass compared to protons and neutrons. So when we say the mass of proton, neutron and electrons in AMU, one proton will be 1.007276 AMU and one neutron is 1.008665 AMU and one electron is actually 0.000549 AMU. So one electron's mass is about 1 by 1836 of the mass of the proton. So the contribution of the electron to the total atomic mass is very negligible. The actual value of 1 AMU is approximately the mass of the single proton or a single neutron, but it is more precise standard based on the carbon-12 atom. Let us define what a mass defect is. When protons and neutrons and electrons to a tiny extent come together to form atom's nucleus, some of the individual masses is converted into energy, which is called binding energy, that holds the nucleus together as per Einstein's E is equal to mc square. This phenomenon, known as the mass defect, means that the mass of the nucleus is slightly less than the sum of the masses of its individual protons and neutrons. Therefore, if you were to sum the masses of 6 individual protons, 6 individual neutrons and 6 individual electrons, it would be slightly more than the exactly 12 AMU. The 1 AMU definition is based upon the actual mass of the bond. It is actually 1/12 of carbon 12 atom, not the sum of unbound constants. Let us now see some fundamental physical constants which are useful to us in the coming portion. Okay, please note down these constants so that this will be useful in your remaining chapters. Okay, now here given speed of light in vacuum was 3 into 10 raised to 8 meter per second, and charge of electron 1.6 into 10 raised to minus 19 coulomb. And gravitational constant is given 6.67 into 10 raised to minus 11 meter cube kilogram raised to minus 1, then second raised to minus 2. Okay, and then universal gas constant is given 8.31 joules per mole Kelvin. Like that, a lot of such constants are given. Please note this down, and this will be useful to you in the coming chapters. Here also some basic units and their conversion are given for your information. So 1 centimeter is equal to 10 raised to minus 2 meter and 10 raised to minus 5 kilometer, or 1 kilometer is equal to 1000 meters. Okay, and like actually 1 Fermi is 10 raised to minus 15 meter, and 1 angstrom is 10 raised to minus 10 meter. Then again 1 square meter is equal to 10 raised to 4 centimeter square. Like that, actually a lot of such conversion factors are given for your information. Please note this down. Similarly, when you come into conversion factors for volume and mass, 1 cubic meter is equal to 10 raised to 6 centimeter cube, and 1 liter is equal to 1000 centimeter cube. Similarly, for mass, if you are going, 1 gram is equal to 1 by thousands of a kilogram, and 1 AMU is equal to 1.661 into 10 raised to minus 27 kilogram. So these are some conversion factors. It contains some other factors also. Please note it down so that it can be used in the later stages. Now we will see the different system of units. There are different systems of unit adopted by different countries. Now FPS means foot pound seconds, but it's a British system of units. Then CGS is Gaussian systems. It is centimeter gram second. MGS is meter kilogram second. Now the currently accepted system is International System of Units, SA unit. It is a modification of MGS system or rationalized MGS system. There are 2 supplementary units also derived. These are radian for the linear angles and steradian for the solid angle. And the 1 radian means actually it is actually that 1 radian is equal to arc length by radius. Okay, now the for making 1 radian, if r is the radius of a circle, and it is making some arc length, if that arc length is equal to r, means the arc length is equal to the radius. When r is equal to arc length, then it is 1 radian, means arc length divided by r is equal to 1. That means arc length is equal to r, then it is 1 radian. 1 steradian is the solid angle. 1 steradian is equal to area, surface area divided by the square of the radius of the sphere. Okay, so if the area, surface area is r square, it is equal to the square of the radius, then it will become 1 steradian. The angle will become 1 steradian at the center. It makes with the center for the sphere. Okay, now the maximum angle that can be formed is 4 pi. 4 pi is the maximum angle that can be made at the center for the sphere. Okay, so you know that one steradian is the formula for steradian is area by r square. Okay, so a full sphere has a solid angle of 4 pi steradians. So when the full angle is 4 pi means 4 pi is equal to area by r square. That means area, surface area of the sphere is equal to 4 pi into r square. Means the angle, full angle is 4 pi. That means the surface area of the sphere divided by r square. Means when you take the full angle, 4 pi steradian you are taking, you have to consider the full surface area of the sphere. Then surface area of the sphere by r square. That means 4 pi into r square is equal to surface area of the sphere. So when length of the arc is equal to radius, radian is equal to radius by radius is equal to 1 radian or 1 rad. So 1 steradian is equal to area by r square. Okay, steradian is equal to area by r square. So a full sphere has a solid angle of 4 pi steradians. Okay, so the figure you can see the angle theta is equal to arc length divided by r. Supplementary unit radian is the plane angle subtended at the center of a circle by an arc of length equal to the radius of the circle. Okay, just now I explained. Then 1 steradian is the solid angle subtended at the center of the sphere by its surface whose area is equal to square of the radius of the sphere. Okay. So if you take the conversion factors, 1 degree is equal to 60 minutes is equal to 1 by 60 minutes into 60 into 60 seconds, that is 3600 seconds, that is 360 by 2 pi radians. The reason is actually 360 at the center of the circle the angle subtended is 360 degree, that is equivalent to 2 pi. Okay, therefore 1 degree is so 1 radian is equal to 360 by 2 pi. 2 pi radian is 360, therefore 1 radian is 360 by 2 pi. Now 1 minute is equal to 1 by 60th of a degree, and 1 second is equal to 1 by 3600 of a degree. Now let us do an example. The moon is observed from two diametrically opposite points A and B on Earth. Okay, you can see the Earth is there, then A and B are 2 points are given. Okay, so when it is watched from moon, A and B point are actually this diametrically opposite points. Then AB is the diameter of the Earth. Okay, now it is the angle subtended by at the moon by the two directions of the directions of observation is 1 degree 54 minutes. The theta is 1 degree 54 minutes. Given the diameter of the Earth is 1.276 into 10 raised to 7 meters. The diameter of the Earth is given. Can be the distance of the moon from the Earth. The distance of the moon from the Earth is actually nothing but the radius of the radius of the angle, of the angle subtended, the arc length actually. It is being the arc length, because actually that even though since it is a very big distance, AB is actually very big, so actually you can consider it as a straight line rather than a curved line, because that the angle is so small, and actually that the distance is very the AB is very long. You can consider it as a straight line. So first let us convert the theta into radians, because actually we are calculating in radians. So we know that 360 degrees is 2 pi radians. So 1 degree is 2 pi by 360 radians. So 1 degree 54 minutes is actually 1 degree plus 54 by 60 degrees. This is 1.9 degrees. So when it is converted into radians, actually 1.9 into pi by 180 radians. Now we know that actually radian is equal to arc length by radius. Okay, and arc length, what is the arc length? Arc length is the diameter of the Earth, that is 1.276 into 10 raised to 7 divided by the distance d. Okay, d is what we wanted to find out. We don't know what is d is. So d is equal to 1.726 into 10 raised to 7 divided by the radian. Okay, arc length is equal the radius is equal to arc length by angle. So length is actually 1.276 into 10 raised to 7 divided by, we have calculated that degree in radians, 1.99 into pi by 180. This is or that means you will get 38.5 into 10 raised to 7 meters. Steradian is the SI unit for measuring solid angles, and for a full sphere it has a solid angle of 4 pi steradians. Then 4 pi is equal to surface area of the sphere by r square. So surface area of the sphere is equal to 4 pi r square. So we know that the solid angle can be calculated, omega is equal to area by r square, where area is the area of the portion of the spherical surface and r is the radius of the sphere. Some examples are illumination. In lighting, solid angles are used to describe the amount of light emitted or received by a source or detector. Astronomy, astronomers use solid angles to measure the apparent size of the celestial objects. In optics and in geometrical optics and all, everywhere this steradian is used. Solid angles are used. We know that the plane angle is a two-dimensional figure, okay, and whereas the solid angle is a three-dimensional figure. Now some examples of solid angles are the light emitting from a torch, or maybe the birthday cap, or the liquid poured from a bottle to a glass, or the colors injected into a balloon filled with water, or a carrot. All these things are examples of solid angles. Small masses are measured using common balance law. For heavy object, we use gravitational methods, and for very light objects, mass spectrography is used. We know 1 AMU is 1/12 of the mass of the C12 atom. So the mass of the electron is in the order of 10 raised to 30 kilogram, whereas the mass of universe is in the order of 10 raised to 55 kilogram. Now we will take the measurement of time. 1 second is taken as the time needed for vibrations of cesium-133 atom. Okay, it's exactly saying time needed for 9192631770 vibrations of cesium-133 atom. 1 minute is, we know that is 60 seconds, 1 hour is 60 minutes, that is 3600 seconds. 1 day is 24 hours, that is 86400 seconds. 1 year is 365.25 days into 24 into 60 into 60 seconds, that is 31557600 seconds. Precise measurement of time is very much important in science. Without precise measurement of time, the GPS system, global position system, we use for world navigation cannot be used effectively. For example, we are using Google Map. Google Map we are using for finding out distances between two places and to find the route to one place. So this GPS is using 18 medium Earth orbit satellite at present. It will which will be enhanced to 24 satellite by about 2027. So India is also having a GPS like system called navigation with Indian constellation. GPS relies on constellation of satellites or a group of satellites in medium Earth orbits to provide global coverage. Theoretically, it requires only 3 satellites to cover the whole Earth, but actually, in practice, up to 7 satellites are used at a time. So, medium Earth orbits of satellites is used to provide global coverage, good geometry of diversity for accuracy, and reasonable signal strength or latency. GPS satellites operate in medium Earth orbits, as I said, at an altitude of about 20,200 km. They have an orbital period of approximately 12 hours, meaning they circle the Earth twice a day. Okay, so it will complete one revolution in 12 hours. So means actually 2 times a day it will cover the whole Earth. There are two more type of orbits for satellites. It's called geosynchronous orbit and geostationary orbits. So GPS systems, global positioning system, does not use geosynchronous or geostationary means satellite. Instead, GPS satellites operate in medium Earth orbits. Geosynchronous orbit means a satellite in geosynchronous orbit has an orbital period that matches the Earth rotational period, that approximately 24 hours. This means that it stays over the same longitude of Earth. Its orbit can be inclined relative to the equator. But geostationary orbits, geostationary orbits satellites are special type of geosynchronous orbit where the satellite is directly above the equator at 0-degree inclination and orbits at an altitude of approximately 35,786 km from the ground. A geostationary satellite appears to remain stationary in the sky. These are commonly used for communication and weather satellites. So for communication and weather prediction and all, the satellite should be seen a stationary position with respect to the country. Then only it can get signal and transmit signal through it for communication and all. GPS systems work by using a network of satellites, a receiver, and algorithms to determine a user's location, velocity, and time. So satellites broadcast microwave signals that GPS receivers pick up to calculate the distance from each satellite. So if you have some mobile device or the GPS receiver, that it will be a microwave receiver. So it will receive the microwave signals, and through this the position or the distance can be calculated. By knowing the distance from at least 3 satellites, the receiver can pinpoint the user's position on Earth. GPS satellites are a constellation of satellites managed by US government which orbits the Earth. Each satellite broadcasts unique signals and orbital parameters. Satellites carry atomic clocks to ensure high precision. Now, GPS receivers such as those in phones and navigation devices listen to the satellite signals. They measure the time it takes for signals to travel from satellite to the receiver, which allows them to calculate distances. Trilateration. With the distance from at least 3 satellites, the GPS receiver can calculate its 2D altitude and longitude positions. By knowing the distance from 4 or more satellites, it can determine its 3D, means the latitude, longitude, and altitude position. The receiver uses the collected data along with the information about the satellite's positions to calculate the user's location. This information is then displayed on the screen or used by other navigation features. Every calculated quantity which is based on measured values will have an error. Uncertainty in measurement of any physical quantity is called an error. Accuracy is how close the measured value to the actual value, whereas precision is how close the measured values to each other. So there can be 2 types of errors: systematic errors and random errors. Systematic errors are those errors which are due to instrumental errors, imperfection in experimental techniques, or personal errors, or it can be due to personal errors also. So to minimize systematic errors, we have to select better instruments and improve the measuring techniques, or we have to follow precautions while measuring. Systematic errors can be the following types: instrumental errors, for example, zero error of screw gauge, vernier caliper, and error in meter bridge, etc. Or there can be personal errors which are due to the observer. For example, parallax error. What is parallax? When you observe a scale, you have to observe that scale or the reading from the top of the needle, not from the sides. If you look at from the sides, you will get another reading. Therefore, to minimize actually the parallax, there will be a mirror under the under this needle, and when you look from the top, there should not be. The image should coincide with the needle. Then there won't be any parallax. Then error due to external causes, due to changes in temperature, pressure, velocity, height, etc. Then errors due to imperfection of the instrument. Okay, imperfection of the experimental methods. Okay, there is also another reason. Systematic errors are usually determinate. So this can be eliminated by taking proper precautions. However, when the sources of errors are not properly identified, the experiment is repeated by different methods. Next type of errors is random errors or irregular errors, or it is also called accidental errors. Those errors which occur irregularly are called random errors. These errors arise due to unpredictable fluctuations in experimental conditions. So the same person taking the measurements, different measurements, in the same physical conditions may get different results, even though the instrument is in very good condition and sensitive one. The observer may be very careful, yet such small differences in the result generally occur. There is no different cause for such errors. The sources are unknown and uncontrollable. Such errors are therefore purely accidental in nature and are termed random or accidental errors. An error that occurs randomly and whose causes are unknown and indeterminate is called random error. We told you that random errors occur due to unpredictable fluctuations in experimental conditions. Least count error, for example, least count error is the error associated with the resolution of the instrument. Okay. So least count is the smallest quantity that can be measured accurately. So in a meter scale, the smallest possible value that can be measured is actually 1 mm. Okay. Therefore, the least count is 0.1. It will be 1 by 10. That will be 0.1. Absolute error, on the other hand, it is the magnitude of the difference between the individual measured values and the mean or true value of the quantity. Okay. Mean value. So when we do multiple events of experiments, that means when you are doing the same experiment multiple times, then mean of the value is equal to adding all the values together and dividing by the number of experiments. If A1, A2, A3 up to N are the values you received in multiple experiments, then A1 plus A2 plus A3 up to N divided by N will give the mean value, A mean or the true value. Then absolute error is the difference of the mean value from each individual value. But in this case, we will take only the magnitude. Sign is not considered. It is the modulus of the difference. So, absolute error is the difference between individual measured value and true value of the quantity. It is given by modulus of delta A. It will be always positive. If A1, A2, A3 up to A10 are the different values of measured of measurement or the measured values, then A mean is equal to A1 plus A2 plus A3 up to A10 divided by 10. Then delta A or absolute error of A1, delta A1 is equal to A mean minus A1, modulus of A mean minus A1. The arithmetic mean of all the absolute errors is taken as the final or mean absolute error of the value of the physical quantity A. It is represented by delta A mean. So if A1, A2, A3 up to AN are the measured values, then delta A1 is equal to A minus A mean, modulus of A minus A mean. Okay. Like that, if you are finding out all the absolute errors for A1, A2, A3, then it will be delta A1, A1, delta A2, delta A3, like the delta AN. So if you add all these absolute errors together and divide by N, you will get the delta A mean, which is the mean absolute error. Relative error is the ratio of mean absolute error to the true value. Relative error is equal to delta A mean by A mean. If A1, A2, A3 up to AN are the measured values, then A mean is equal to A1 plus A2 plus A3 up to AN divided by N. Then delta A mean or the relative error is equal to modulus of delta A1 plus modulus of delta A2 up to modulus of delta AN divided by N. Then there is percentage error. Percentage error is the relative error in terms of the percentage. So relative error into 100 will give the percentage. So percentage error is equal to delta A mean by A mean into 100 percentage. So when the relative error is expressed in percentage, it is called the percentage error. So percentage error, as I told you, delta A mean by A mean into 100. When we do the measurement of the physical quantities, there can be combination of errors. So how these combinations of errors are handled? So there are different rules for handling these errors. Rule 1, when two quantities are added or subtracted, the absolute error in the final result is the sum of the absolute errors in the individual quantities. For example, if two quantities x and y add up to form another z, then delta z, the absolute error of z is the sum of the absolute errors of individual physical quantities x and y. That means delta z is equal to delta x plus delta y. Same is the case of subtraction also. If it is subtracted, delta z is equal to delta x minus delta y. Second rule, when two quantities are multiplied or divided, the relative error in the result is the sum of the relative errors in the multipliers. If two quantities x and y are multiplied or divided to form another z, then delta z by z, the relative error, is equal to delta x by x plus delta y by y. Rule 3. The relative error in the physical quantity raised to the power k is k times the relative error in the individual quantity. For example, if z is equal to x raised to k, then delta z by z is equal to k times delta x by x. So when two quantities are added or subtracted, the absolute error in the final result is the sum of the absolute errors in the individual quantities, as we discussed earlier. Let x is equal to a plus b or a minus b. If the measured values of the two quantities a and b are a plus or minus delta a and b plus or minus delta b, then the maximum absolute error in the addition or subtraction is equal to delta x is equal to delta, plus or minus delta a plus delta b. Error in multiplication or division. So let x be a into b and x is equal to a by b. If the measured values of a and b are a plus or minus delta a and b plus or minus delta b, then the maximum relative error in x is equal to delta x by x is equal to plus or minus delta a plus delta b by b. Errors in the case of quantities raised to power. The relative error in a physical quantity raised to the power of k is k times the relative error in the individual quantity. Suppose x is equal to a raised to k, then delta x by x is equal to k times delta a by a. Let us summarize the combination of errors. For x is equal to a plus or minus b, then delta x is equal to plus or minus delta a plus delta b. Case 2, for x is equal to a into b, delta x by x, the relative error is equal to plus or minus delta a by a plus delta b by b. For x is equal to a by b, it is the same. Delta x by x is equal to plus or minus delta a by a plus delta b by b. For x is equal to a raised to n b raised to m divided by c raised to p, then delta x by x is equal to n times delta a by a plus m times delta b by b plus p times delta c by c. Let's consider one example. In successive measurements of period of oscillation of pendulum, the readings are 2.63, 2.56, 2.42, 2.71 and 2.8 seconds. Calculate the absolute errors, relative error and percentage errors. So first we have to find out the mean of the measured values. For that we have to add all the values together, that mean, and we have to divide it by the number of experiments. Now let it be, now when we add actually 2.63 plus 2.56 plus 2.42 plus 2.71 plus 2.8 divided by 5 will give 2.62 seconds. Now we have to find out the find out the errors. So to find out the relative error, modulus of delta A1, we have to subtract each individual value. We have to subtract the mean value from each individual value. For delta A1 is equal to modulus of A1 minus 2.62. Like that we have to find out delta A2, delta A3, delta A4 and delta A5. Now if you take the average of or mean of all the relative errors, you will get the mean relative error. And if that value is multiplied by 100, you will get the percentage error. Let's take another example. Find the relative error in G, where t is equal to 2 pi root Lg. So t is equal to 2 pi root of L by G. So t square is equal to 4 pi square into L by G, which gives G is equal to 4 pi square into L by T square. Therefore, the relative error delta G by G is equal to delta L by L plus 2 into delta T by T. 4 pi square being a constant, it is ignored. Let us now see the Greek alphabets and which are commonly used in physics. So there are capital and lower cases are given here, and alpha, for example, alpha is the first letter and it is used for angular acceleration, linear expansion coefficient, alpha particle and fine structure constant. Beta is used for beta particle and sound intensity. Gamma is used for gamma ray, ratio of heat capacities, relative stick correction factor and shear strain. Delta, capital delta and small delta are widely used. Delta is used for change in some quantity. Epsilon is used for emissivity, strain, permittivity and EMF. Zeta is not commonly used, and eta is used for efficiency and viscosity. Theta is used for angle and temperature. Then iota, the lowercase iota is rarely used, where capital iota is sometimes used for the identity matrix or moment of inertia. Kappa is used for spring constant and dielectric constant. Lambda is for wavelength, thermal conductivity constant, then eigenvalue of the matrix, then linear density. Mu is used for coefficient of friction, electrical mobility, reduced mass and permeability. And nu is used for frequency. Xi is used for damping coefficient, omicron is not used commonly. Then pi is used as a product symbol and as a circle number. Rho for volume density and resistivity. Sigma, capital and small both are used. Capital is used for sum total. Then small sigma is for Boltzmann constant, electrical conductivity, uncertainty, stress, surface density, etc. Tau is used for torque, tau particle, time constant, shear stress, etc. Epsilon is used as mass to light ratio. Phi is a magnetic or electric flux, and it is also used for angle. Chi is Rabi frequency, susceptibility, mole fraction. Psi is used for wave function. Omega is used for, capital omega is used for ohms, and the small omega is angular velocity, used for angular velocity. Let us see some standard symbols and units. So acceleration is actually, the unit is at the meter per second square or meter second raised to minus 1. Then acceleration of free fall is g, it is meter second raised to minus 2. Then activity of radioactive source is a second raised to minus 1. Amplitude is in meter. So all the items are given here. Okay, atomic mass unit is given in mu in kg. So angular frequency 2 pi f is given in radian per second or radian second raised to minus 1. So all the standard symbols and units are given. Please note it down. It will be useful for you in the coming sessions. So the unit for Boltzmann constant K is joule K raised to minus 1. Then bulk modulus K is in Pascal, capacity is in Farad, then charge is coulombs, then conductance is ohm raised to minus 1. Here also all the, here also many constants are given, details of constants are given. Please note these constants. Density rho is in kilogram meter raised to minus 3. Diameter is in meter. Displacement is also in meter. Distance is in meter. Efficiency has no units. Then electric field strength is volt meter raised to minus 1. Charge is in coulombs. Then EMF is in volt. Potential is also in volt. Electron mass is in kilogram. Energy in joules. Electron volt in EV. Then force is in Newton. Focal length is in meter. Then a force constant in Newton per meter, and frequency is in hertz. Then illumination is in lux. Image distance is in meter. Impedance in ohms. Then intensity in watt meter raised to minus and watt per meter square. Kinetic energy in joules, latent heat in joules. Then magnetic field intensity in ampere meter raised to minus 1. Now magnetic flux in Webers, magnetic flux density in Tesla. Then molar gas constant in joules per Kelvin per mole, or joules Kelvin raised to minus 1, mole raised to minus 1. Same as molar heat capacity. Then mutual inductance in Henry, neutral mass in kilogram, normal stress in Pascal. Then number per unit volume is in meter raised to minus 3. Object distance in meter. Then permeability Henry per meter. Permeability of free space mu0 in Henry per meter. Permittivity epsilon in Farad per meter. Then epsilon 0 mean permitted to free space is also in farad per meter. Then angle, phase angle is in radian. Then Planck constant is h in joule second. Then potential difference in volts. Then potential energy in joules. Power in watts. Pressure in Pascal. Then reactance in ohms. The refractive index has no units. The relative atomic mass, relative molecular mass, relative permeability, relative permittivity, all has no units. Since it is a relative quantity, it's a ratio of two quantities of the same unit. Therefore, there will not be any unit for this. Resistance is in ohms, resistivity is in the ohm meter, self-inductance in Henry, then shear stress in Pascal. Then speed and velocity in meter per second or meter s raised to minus 1, or speed of electromagnetic waves is also in meter second raised to minus 1. So strain has no unit, stress is Pascal in Pascal, surface tension Newton meter raised to minus 1. So temperature is in degrees Celsius or Kelvin. Kelvin, when you are saying Kelvin, you should not use any word degree in front of that. It is only Kelvin, there is no degree in that. And when you say centigrade, it should be degree centigrade. Then temperature coefficient resistance is K raised to minus 1. Tension is in Newton. Time constant in seconds. Torque in Newton meter. Triple point is in Kelvin. Then unified atomic mass constant is in kilogram. Velocity meter second raised to minus 1. Viscosity in Pascal second. Volume in meter cube. Wavelength in meter. Work energy in joules. Work function in volts. Young's modulus in Pascal. Now let us see some commonly used constants. Speed of light in vacuum is 3 into 10 raised to 8 meter per second. Permeability of a vacuum mu0 is equal to 4 pi into 10 raised to minus 7 Henry per meter. Permittivity W0, permittivity of free space or vacuum is 8.85 into 10 raised to minus 12 farad per meter. So the charge of an electron is 1.6 minus 1.6 into 10 raised to minus 19 coulombs. Then Planck constant is 6.63 into 10 raised to minus 34 joule second. Then AMU, 1 AMU is 1.66 into 10 raised to minus 27 kg. Mass of electron is 9.11 into 10 raised to minus 31 kg. So mass of proton is 1.67 into 10 raised to minus 27 kg. Molar gas constant 8.31 joule per Kelvin per mole. Avogadro number is 6.02 into 10 raised to 23 per mole. Boltzmann constant is equal to 1.38 into 10 raised to minus 23 joule per Kelvin. Gravitational constant G is equal to 6.67 into 10 raised to minus 11 Newton meter square per kilogram square. Acceleration of free fall G is equal to 9.81 meter per second square. Let us see what are significant figures. Every measurement involves error, and the result of measurement indicates the precision of the instrument used for measurement. Normally, the reported result of measurement is a number with the digits reliably known and the first digit that is uncertain. The reliable digits plus the first uncertain digit are known as significant digits. If the period of, for example, if the period of oscillation of a simple pendulum is 1.62 seconds, then the digits 1 and 6 are reliable and certain, whereas 2 is uncertain and the number of significant figures is 3. Including more digits than the significant digit will be superfluous and misleading, as it would give a wrong idea about the precision of the instrument. All reliable digits plus the first uncertain digit will give the significant figures. Significant figures indicate the precision of the instrument used for measurement, which depends on the least count. The least count of a measuring instrument is the smallest value that the instrument can accurately measure. It represents the smallest increment of measurement that can be reliably read or estimated on the instrument scale. Essentially, it is the precision of the instrument. Least count is equal to value of one division on the main scale divided by number of divisions on the secondary scale. For example, if you are using a meter scale for measurement or the scale in your instrument box, so the smallest value that can be measured is only mm. Therefore, the least count will be 1 by 10. 1 by 10 will be 1 by 10 will be 0.1. 0.1 will be the least count of the meter scale. Now, change of unit will not change the number of significant digits in a measurement. For example, 2.308 centimeter is same as 23.08 mm or 0.02308 meter or 23080 micrometer. All have 4 significant figures. Thus, the location of decimal point shall not determine the number of significant figures. Let's see some of the rules for determining significant figures. All non-zero digits are significant. For example, 123.45 has 5 significant figures. Zeros between non-zero digits are significant, no matter where the decimal point is. Example, 102.03 has 5 significant figures. Leading zeros at the beginning of a number are not significant. They only act as placeholder for the decimal point. That is, if the number is less than 1, the leading zeros on the left of the first non-zero digit or the zeros on the right of the decimal point are not significant. For example, 0.0056 has only 2 significant figures, 5 and 6. 0.002308 has 4 significant digits. Terminal zeros or trailing zeros at the end of the number are significant if the number contains a decimal point. For example, 12.500 has 5 significant figures. The zeros after the decimal is also considered here. And 3.500 or 0.06900 have 4 significant figures each. 100 point has three significant figures. 100 point. The decimal point indicates that the zeros are significant. Trailing zeros in a whole number with no decimal point are generally not significant. There can be ambiguity as they might just be placeholders. For example, 1200 might have 2 significant figures, 1 and 2. To avoid ambiguity, we have to use scientific notation. For example, 1.2 into 10 raised to 3 has only 2 significant figures. 1.200 into 10 raised to 3 has 4. 123 meter is equal to 12,300 centimeter or 1,23,000 millimeter. This all has only 3 significant figures. Other trailing zeros are not significant. Also, 4.700 meter is equal to 470.0 centimeter, 4,700 millimeter, 0.004700 kilometer all have 4 significant figures. To remove ambiguity, it's always better to use scientific notation in the power of 10. Exact numbers have an unlimited number of significant figures. These are numbers that are defined or counted and not measured. For example, 1 meter is 100 centimeter. Both 1 and 100 have an unlimited number of significant figures in this definition. The multiplying or dividing factors, which are neither rounded numbers nor numbers representing measured values, are exact and have infinite number of significant digits. For example, r is equal to d by 2 or s is equal to 2 pi r. Here 2 is an exact number and can be written as 2.0 or 2.00 or 2.0000 as required. Similarly, in half mv square, 2 is an exact number. Now let us see how numbers are expressed using scientific notations. So every number can be expressed as a into 10 raised to b, where a is a real number between 1 and 10. That's called significant or mantissa, and b is the a positive or negative integer exponent. So thus 4.700 is equal to 4.700 into 10 raised to 2 centimeter. 4.700 meter is equal to 4.700 into 10 raised to 2 centimeter, or 4.700 into 10 raised to 3 millimeter, or 4.700 into 10 raised to minus 3 kilometer. Here the significant figures all are 4 in these cases, and the power of 10 is irrelevant in determining the significant figures. Also, all zeros appearing in the base number in the scientific notations are significant. The scientific notation is ideal for reporting measurements. We many times come across very small quantities and big quantities in physics. To express these numbers, we use scientific notation, which employs the powers of 10. So in scientific notation in computer normally is used as, as expressed as 3 point, for example, 3.56 into 56 E9. For exponentiation we are using E, or maybe 4.92 E minus 7, like that. E stands for exponent of 10. In some calculator, instead of E, a space is given. When dealing with very large or very small measurements, we use prefixes as shown here. So we know that actually 10 raised to 1 is deca, 10 square is hecto, 10 cube is kilo, 10 raised 6 is mega, 10 raised 9 is giga, 10 raised 12 is tera, 10 raised 15 is peta, 10 raised 18 is exa, 10 raised 21 is zeta, 10 raised 24 is iota. So coming down, 10 raised minus 1 is deci, 10 raised minus 2 is centi, 10 raised minus 3 is milli, 10 raised minus 6 is micro, 10 raised minus 9 is nano, 10 raised minus 12 is pico, and 10 raised minus 15 is femto, 10 raised to minus 18 is atto. Like that it goes. Each prefix represents a certain power of 10. For example, 1.9 as 1.27 into 10 raised to 9 watts is actually 1.27 gigawatts. 2.35 into 10 raised to minus 9 seconds is equal to 2.35 nanoseconds. Let us see some more examples. 25.3 centimeter is having three significant figures, all non-zero. 1.05 meter will have 3 significant figures. The 0 between 1 and 0 is significant. 0.02 kilogram has only one significant figure, as the 0 in 0 here is not significant. So 10.0 has 3 significant figures, as the trailing zeros after the decimal point are significant. 500 is ambiguous. It can be the significant figures can be 1, 2 or 3. If it is estimated to the nearest 100, it is 5 hundreds. If it is estimated to the nearest 10, it is 2 significant figures. If it is estimated to the nearest unit, it has 3 significant figures. To be clear, it should be written in scientific notation as 5 into 10 raised to 2, which has only one significant figure, and 5.0 into 10 raised to 2 has 2 significant figures, and 5.00 into 10 raised to 2 has 3 significant figures. 3 into 10 raised to 4 seconds has only 2 significant figures. The zeros in the scientific notation are not counted unless they are after the decimal point. 0.00780 has only 3 significant figures. leading zeros are not significant. But the trailing zeros after the non-zero digits are and the decimals is significant. Order of magnitude. To get an approximate idea of the number, we may round off the number to 1, where the number is less than or equal to 5, and to 10, where it is greater than 5 to 10, up to 10. Then the number can be expressed approximately as 10 raised to b, in which b is called the order of magnitude of physical quantity. When only an estimate is required, the quantity can be expressed as order of magnitude in 10 raised to b. For example, diameter of earth is 1.28 into 10 raised to 7 meter. That is, in order to see, that's in the order of 10 raised to 7 meters. Since it is 1.28, it is less than 5, therefore that will be ignored. That will be considered as 1. So it has an order of magnitude 7. The diameter of hydrogen atom is 1.06 into 10 raised to minus 10 meter in the order of 10 raised to 10 meter with the magnitude of the order minus 10. And the diameter of earth is 10.7 by 10 raised to 10 is equal to 10 raised to 17. That is 17 orders of magnitude larger than the hydrogen atom. Rules of arithmetic operation with significant figures. The result of the arithmetic calculation of measured values cannot be more accurate than the original measured values on which the result is based. In multiplication and division, the final result should not have more significant figures than the original data from which it was derived. For example, m is equal to 4.237 gram and v is equal to 2.51 centimeter cube. Then the density, mass per volume, volumetric density is equal to 4.237 divided by 2.51, and the result should have only 3 significant figures, because the denominator is the minimum significant figures in the division is 3. 2.51 has 3 significant figures, whereas 4.237 has 4 significant figures. So we will take the least significant figure. So even though the result has 11 decimal places like 1.6880478086 gram per centimeter cube, we will consider only 3 significant figures that will give 1.68, but actually the next figure is 8, therefore we will round it off to 1.69. Hence it shall be of the 3 significant figures 1.69 gram per centimeter cube following the least significant figure of the original numbers. Speed of light in vacuum is equal to 3 into 10 raised to 8 meter per seconds. Only 3 significant figures, 3.00. Light year is equal to 3 into 3.00 into 10 raised to 8 into 365.25 into 24 into 60 into 60. So that is the distance traveled by light in 1 year. So the result can have only 3 significant figures. So that will be 9.47 into 10 raised to 15 meter. But in the case of addition or subtraction, the final result should retain as many decimal places as are there in the number with the least decimal places. So for example, 436.32 plus 272.2 plus 0.301. So the first first number is having 2 decimal places, and second one is 1 decimal place, and third one is 3 decimal places. But if the least decimal place is 1, therefore the result should also have only 1 decimal place. So even though the result is 663.821, we will consider it as 63.8, since we have to take only 1 decimal place in this case. Again, 0.307 minus 0.304 will have 0.003, that is equal to 3 into 10 raised to minus 3 meter. For addition or subtraction, the rule is in terms of decimal places, not in terms of significant figures. Now let us consider rounding off. the preceding digit is raised by 1 if the insignificant digit is greater than 5 and left unchanged if it is less than 5, rounding down. If the insignificant digit is 5, where the preceding digit is even, then the insignificant digit is not considered. If it is odd, it is raised by 1. For example, 2.746 is rounded to 3 significant digits. It is 2.75 because the insignificant digit 6 is more than 5. For 1.743, it will be 1.74 since the insignificant digit 3 is less than 5. Also 2.745. Here the preceding digit is even, therefore it will be rounded to 2.74. And in 1.935, it will be rounded to 1.94. Let us consider an example. Calculate the surface area of a cube where each side measures 7.203 meter. We know surface area is equal to 6a square, 6 into side square. That is 6 into 7.203 into 7.203, which will give 311.299254. But there are only 4 significant figures. Therefore, we have to limit it to 4. Therefore, it is 311.3 meter square. Now, with this actually, we are completing the theory portion up to significant figures. Now, in the next part, we will be considering dimensional analysis.